Okay, so here ability to draw the band diagram of MOSFET along the channel direction, and when the gate voltage increase and drain voltage increase. So let's do that. So here we show MOS. This is along the gate direction. That means from gate to the channel. But we can also draw from the source to the drain direction of the band diagram. It will be something like this. Because we have two p-n junction back to back, and the source is N. This is for NMOS, and your channel is P. And the gate voltage, when you apply gate voltage for the NMOS, you apply positive voltage to push down the band. So that means this barrier of between the source to the channel will be reduced. And also when you apply the drain voltage, then the drain side will also be pushed down. So eventually, if you apply both gate voltage and the drain voltage, then the band will look like something like this. So first, this barrier is reduced, so you have electrons jump over. So you can have the electrons diffuse over the barrier, and once it reaches this downhill, it will be accelerated by the drain voltage, and it will fall down, and then eventually collected by the drain. So this is how the current flow in the MOSFET. And then ability to determine the MOSFET operation region, cutoff, triode, linear, or the saturation, and then calculate the drain current based on those regions. So let's look at the IV equations. So when the gate voltage is smaller than threshold, this is cut off, and to the first order, the drain current is almost zero. But if we consider the sub-threshold current, then there will be very small current, and it's given by this I0 exponential Q and gate voltage divided by MKT. M is the body factor. It's a coefficient. And then when the gate voltage is larger than threshold, then we can divide this into triode or the saturation. The turning point is you need to compare the Vg minus Vt versus the Vd. So if Vg minus Vt larger than Vd, then we have the triode, and you use this equation. And then if we have the saturation, then you use this equation. So here in the saturation, and because we have Vg minus Vt squared, so this is also called the square law. And then draw the IDVG and IDVD plots. Okay, so this is also important. IDVD. It looks like this. So this is the turning point where the Vg minus Vt equals to Vd. And this is the triode. And this is the saturation region. This is at the given Vg. If we consider the channel length modulation effect, then this will no longer saturate. So if you consider the channel length modulation effect, and then we can also have the IDVG. So this is your threshold, and then this is the turning point, which is also Vg minus Vt equals to Vt, and this is your triode, and this is the saturation, this is your off. Since this off, if we consider the sub-threshold, this is too small, and if you want to visualize, you have to draw the log scale of the ID. Then versus this Vg, you will have this. And this is again your threshold voltage. And below threshold, there is a exponential decay of the current. And this is the subthreshold. And we call this subthreshold slope S. And we say that S is larger or equal to 6 millivolts per decade. What does this mean? This means if you want to reduce your current by 1 order of magnitude, by 10 times, you need to reduce your voltage, gate voltage, by 60 millivolts. So this is the slope. And then we talk about the on current and off current definition. So on current is here. That is the maximum current you can have. And off current is here. That is the minimum current. And the condition for the on current, if you look at the definition here, on current is when the VGS equals to VDS equals to VDD. So both gate and drain equal to the power supply. And for the off current, it's defined as when the gate voltage is 0, but the drain voltage is VDD. So you still have the current flow from the drain to source. And this is the off current. And off current is this one. So to answer one of the questions before, if you have lower temperature, you will see the slope will be steeper and your I off will decrease. And on current, of course, depends on the parameter because on current is the saturation current here. So if you use the saturation current, you will see the on current dependence of the mobility and those parameters and VDD. And then for the off current, one more thing. Okay, I just realized we need to consider one dependency of the off current. That is VT. So if you shift the VT to the right, then if you don't change the S, then you will have the same slope. You have the same slope. Again, that means the off current will decrease. You see the VT increase, off current decrease. So you can use this plot to visualize how the off current change if you change the VT, if you change the subthreshold slope. So I got one question. When we talk about the on and off current, they are only for subthreshold current. No, so for off current, we are talking about this one. This one is the subthreshold current. When we talk about on current is for this saturation current. You need to use this saturation equation for the on current. So on current is not subthreshold. On current is above threshold. Okay. So this is the IV. And then we discuss this subthreshold slope. On current is saturation current, yes. So we talk about the CMOS inverter. And the CMOS inverter, first thing is the voltage transfer curve. And understand the noise margin and the VM voltage. So we need to think about the VTC, voltage transfer curve, input voltage and output voltage. So inverter, you have input voltage and output voltage. And we have this kind of transfer curve. So the Vm is when you define the input equals to the output voltage. This is Vm. And we have this matched condition. if Vm equals to half VDD. So what is this matched condition? So matched condition is here when the threshold voltage NMOS and PMOS are the same, and this parameter like Kn prime, which is mu1 COX times W over Ln equals to mu P COX W over Lp. And in other words, the W over L ratio should be inversely proportional to the mobility ratio, Wp over Wn equals to mu n over mu p. So this is the matched condition. So once you have the matched condition, then the Vm voltage will be in the middle. But if it's unmatched, then you need to use this equation to calculate the Vm, where you can have this ratio of this beta, which is this mu COX W over L. You need to plug in n or p for the NMOS and PMOS respectively. So you can use that for the Vm if it's unmatched. And then for the noise margin, if you use the square law IV relationship, you can calculate the noise margin using those equations here. And this just depends on the VDD and the threshold voltage. But if you look at the noise margin by definition in the VTC curve is here. When this slope is -1, so this one is the noise margin for the input low. And similarly, you have noise margin for the input high. So this is the VTC curve. And then we will have the unmatched case. Depends on the relative strength of NMOS and PMOS. This VTC curve will shift to the left or shift to the right. For example, we can have the, let's say, so this W over L P equals to 1 and W over L N equals to 1. So you know in this case, in this example, the NMOS will be stronger because NMOS, you know, the mu N is larger than mu P. So if you have the same W over L, so NMOS will be stronger. If NMOS is stronger, that means this VTC will shift to the left and the Vm will shift to the left. Because NMOS is for pull down, and if NMOS is stronger, so you will pull down the output earlier. So you will shift to the left. So understand the VTC and the shift depends on the, let's say, the NMOS and PMOS relatively, which one is stronger. The strength depends on the W over L. And then calculate the delay of a CMOS inverter. So there are two methods. One is this average current, and one is RC equivalence. So in the average current, so here the high to low transition, which is for NMOS pull down, is the C VDD divided by 2 and I average. So the average current is average between the initial and final points. So the initial point is when the input gate voltage equals to the drain voltage equals to VDD. So the final point is when the input gate voltage equals to VDD, but the drain voltage equals to half VDD. So you get the saturation current and the threshold current, and then take the average. So you can plug in here, and then you can get the TPHL. And similarly for the TPLH, which is PMOS, is working. So this is the average current method. And if you want to simplify this, you can just think the transistor as a resistor. So you have RC, time constants, and then we have coefficient 0.69 for this transition when the voltage changes by 50%. So here we have one example on the CMOS inverter gate sizing. So this is when one inverter is driving another inverter. So if we want to increase the, let's say, the size of the first inverter by the factor of S, then the delay will change in the in following this formula. So here we can consider, or let's say divide the cap into two components. One is the cap associated with the first inverter. One is the cap associated with the second inverter, which is external to the first one. So if you do that, then the RC delay from the first inverter will remain the same, because when you increase the size, then the cap increase, but the resistance, equivalent resistance decrease. So the RC delay to the internal delay will be the same. But to the external delay, because the cap doesn't change, but the resistance, equivalent resistance of the first inverter decrease by S. So the delay of this component will decrease by S. Okay, and then we talk about the energy and power of the inverter. And there are two contributions to the power. One is this dynamic or active power. This is due to the switching. The input is switching from 1 to 0 or 0 to 1. Then this inverter is driving the cap, and then you are charging and discharging the cap. And also the current is flowing from the VDD to ground during the transition. So you have that short circuit current. So this dynamic switching energy in one clock cycle is CVDD squared. So this is the total energy. And in those two edge, one rising edge, one falling edge, you will have half of the energy. But in total, is CVDD squared. And then the active power will be CVDD squared multiplied by the frequency of the clock, F. So here we assume that the clock switch, the input switch every clock. But if not every clock, then you can add this activity factor alpha in front of that, which is the probability of the switching. Let's say 50% of the clock switch. So you need to multiply by that 50%. So this is dynamic energy and power. And then the other contribution is the static leakage power. So this is when the input stays, let's say, stay at 1 or stay at 0. There's no switching. If there's no switching, so due to the leakage, for example here, the CMOS inverter. So if the input is, let's say, 1, this is VDD, so this is VDD. So this output is 0. So for the PMOS transistor, you see this is VGS for the PMOS. So VGS is 0 actually, but the VDS is non-zero. So you have I-off current for the PMOS. So this I-off current multiplied by the VDD will give you the static power for this inverter. So any questions?